strength or stresses, but we will also do this in different segments. We know for a fact that laminates, when you build them in strange stacking sequences, they can have a lot of coupling terms that will start coupling the in-plane normal stresses and normal strains to shear. So in-plane shear, this normal stress and displacement coupling. Then you can have bending stretching coupling that you can actually try to bend the laminate. It will also elongate or shorten in the other direction based on these coupling terms, or you can try to stretch it and it will start bending by itself or start curving. So that's the bending extension coupling. That's the entire B matrix. And then there are two other coupling terms that are important. They are bending, twisting curvatures, D16 and D26 terms. But at the end, a lot of things can be coupled. So what we're going to do in the first phase, we're going to actually assume the state of stress and deformation stress state to be planar, in plane. And then we're going to look at level stresses, and then we're going to compute stresses in the principal material directions. So this is basically what we're talking about. This is this big red box is the complete coupling equations that in-plane stress resultants Nx, Ny, and Xy are expressed in terms of in-plane, mid-plane also, in-plane and mid-plane strains, epsilon x, epsilon y, gamma xy. And then if there is B matrix, those will be coupled also to kappa x, kappa y, kappa xy. But the first assumption that we make is we say let the laminates be always mid-plane symmetric. As soon as you make this assumption, mid-plane symmetric laminates, this B matrix goes to 0, but that doesn't mean that D and kappas can be 0. It's just in-plane stress resultants are decoupled from bending stress resultants or moment resultants. So in fact, we can still have a set of equations that will say bending moment resultant Mx, My, and Xy are actually expressed in terms of these and the matrix terms in kappa x, kappa y, kappa xy. But we make the other assumption that there are no out-of-plane deformations applied to the laminates, no bending of the laminates. Everything is in the plane of the laminates. So that's the second assumption that gets rid of this. And the resulting equations are basically this, that Nx, Ny, and Xy are only in terms of in-plane stiffness properties A11, A12, to 16, all the way to 66, and then mid-plane strains epsilon x naught, epsilon y naught, gamma x y naught. Now, these matrix properties, if the laminate is also, besides being mid-plane symmetric, if it's balanced, meaning that for every plus angle orientation, there's a minus angle orientation of the same orientation angle, then these terms will also go to 0, A16 and A26, but we don't have to. We can leave them as they are for the time being. Okay? So with this, what we need is to be able to actually solve for the stresses, because these are in the laminate. Remember now, this is a large number of layers potentially. 32 layers or 64 layers or 120 So 200 layers. And these are just the integral of the stresses. Each one of these is the integral of the stresses associated or appearing in each of the layers. So Nx is the integral through the thickness of all the stresses in individual layers in the extraction. Sigma x integral from minus h over 2 to h over 2, h is being the total thickness of the laminate. Which reminds me, I actually forgot to specify the layer thickness in the homework problem. So when I come to the homework assignment, remind me to actually specify the layer thickness. So with this, what do I need to do with this equation? What I need is to go back to how I actually came up with these quantities and look at the stresses. So these quantities, Nx, Ny, and Xy, are the integral of the stresses. That means in each layer, there's a stress. And those, I can go and write those stresses in each layer for the kth layer with their reduced transform stiffness matrix, Q bar of that layer, times the epsilon x, epsilon y, and gamma xy. Now, here, I didn't put a subscript k, but really, this is actually the strain for that particular layer. But something that we said, and my slide doesn't show the raising of those quantities, but the strains in each layer, if I leave the midplane, is equal to the midplane value plus z times the kappas, the curvatures. But in my case, in this particular case, kappas are also 0. So I should do one more thing here. Take this and paste it here. And basically say that, hey, by the way, guys, these are also 0. Because we're looking at the in plane. So whether I show this or not, the layup, when it expands in the x direction or contracts in the y direction or experience shear, every layer through the thickness is experiencing the same level of strain as the midplane strain. So I leave this out as epsilon x, epsilon y, gamma xy, and these actually, I can put these very easily also here, that these terms will disappear. So whatever the midplane strains are related to the individual layer stresses, or individual layer stresses can be obtained by multiplying these quantities with the Q bar matrix properties for that particular layer. So each layer has a different Q bar matrix. Therefore, each layer has different sigma x, sigma y, tau x, y. Okay. Now, what I need to do, if I actually do this analysis and come up with sigma x, sigma y, tau x, y in the layer, or this, I can compute the other one. So one can be computed the other one. And once I have the stresses in the xy, tau xy shear stress directions, then I need the stresses along the principal material directions. And that will be equal to these equations. We have covered these equations. Sigma 1, sigma 2, tau 1, 2 is the transformation matrix. where m is the cosine of the angle, and n is the sine of the angle of that particular layer. This is the transformation matrix multiplied by the stress state. So once I have the stresses in the individual layer, I can go to the principal stress direction. This is important because they are to be used to assess the failure. We will hardly ever use sigma x, sigma y, tau x, y to assess failure of an individual layer. If the material was isotropic, we will compute something like principal material direction stresses, but they are actually called principal stresses. So they'll be sigma 1, sigma 2, tau 1, 2, but that's the Mohr circle that will give you the largest normal and largest shear stresses in the domain. Whereas in the composites, we're not interested in those principal stresses. We don't use Mohr circles because we know for a fact that the matrix is very weak. It's going to start cracking. So stresses have to be checked along the fiber direction and perpendicular to the fiber direction. That's the reason why we're going to be checking sigma 1, which is the stress along the fiber direction, and sigma 2 perpendicular to the fiber direction. And this is the in-plane shear stress in that plane. So now, how do we use these? What kind of problems we will be encountering? And to demonstrate that, I actually separated into two cases. One is a trivial case where I call, okay, sometimes we can have uniform stress state in a laminate across the domain of the laminate. But more than often, stress state is complicated. That was homework number 2, that I said, okay, here's a plate with far field stress resultant acting n sub x bar and n sub x bar on the other side, stretching it. Because of the existence of the hole, the distribution of the stress resultants in this laminate are complicated. They are not uniform. Now, far from the hole, the stress state at point A might be somewhat uniform over here and over here as I go up and down along this boundary. That NX state might be almost same as the NX bar. As I move away from the applied stress resultants far from the edge, as I get closer to the hole, right at the hole, there cannot be any stresses in the X direction. And since deformation pattern is also somewhat strange here, that there will be probably some normal stresses in the Y direction here, whereas here there's no normal stress in the Y direction. Only at point B you may be able to experience that. If you move around the hole, the sigma x will start increasing as you come close to this edge, and there it's actually going to reach the maximum because of stress concentrations. It's going to be actually even larger than NX bar. So at point C, NX will be larger than NX bar. And in your homework problem, there was we said internal stress is sigma x. Sigma x was actually quite large, 3 times what you would get over here. With that, also shear stress is going to start increasing as we go along here. And right there, it may go back to 0 because this is a free boundary and there cannot be any stress in the x direction here at point C in shear NXY. But somewhere in there, NXY will be, NXY will become maximum. But to be able to do this analysis, we will need to do a bunch bunch of other things. We're not doing that right now. You can go and put this into your finite element analysis package and do a finite element analysis of this. But this course is not to teach you finite elements, although at some point we will be using finite elements just to show that you can also use finite elements in design. But we're going to first go to the case of simple, a uniform stress state. So this plate has no hole, uniform stress distribution inside, and boundary conditions do not restrict to create boundary layers. And in general, this plate can have applied the stress resultants, NX bar here and here, and Y bar, okay, and that's in here, applying in the positive direction, stretching in that direction, Y bar, and uniform along that edge, uniform along this edge. And then the shear stress applied to NX Y bar, and that is, I showed it as positive here, where it's acting up here, down here, and to the right, and to the left here. So each of these can be controlled differently as applied stress resultants. And inside every point, NX is equal to NX bar. In fact, I should be writing this in some sense a function of x comma y. Okay. So NX is actually a function of x and y coordinates. So it's here. X comma y. And so is an xy. Function of x comma y. But because of the uniformity of everything, no restricting boundary conditions, no internal discontinuities, the distribution of nx, ny, and nxy is uniform and is equal to the applied stresses. Incidentally, this will become our homework assignment that we'll put up today. And then for a given laminate, we'll be needing the stresses in each layer in this plate. Now, here on the other hand, there's again a distribution of nx, ny, and nxy. But these are complicated and not even, I need to be able to put a little bar over it. Let me see if I can insert an equation there. And the equation should have not equal. And not only not equal, but can be quite complex, depending on the intrusion or stress discontinuity or boundary conditions. You might say, okay, I'm applying NX here, but I also don't want the plate to deform in the transverse direction because I'm using grips in the fixture and pulling it apart. So if I put the grips and bolt these edges down and pull it apart, the inner section might want to go in. So right around here, there will be a stress boundary layer due to the boundary condition of not letting V displacement along this edge to be non-zero. We will assume them to be zero. So what do we do if you have this kind of a thing? What are you going to be doing? What we will be doing is this, which takes us to analysis. So the first thing is we have to write the plate governing equations for the plate and for the in-plane. And the governing equations for simple, uncoupled, without bending, I mean, plate equations are these, that the derivative of nx, sometimes I use nxx since I use nxy on the other symbols. Nx and nxx are the same thing in my notes and in my lectures. Variation of the nx along x direction plus variation of nxy in the y direction must be equal to 0. This is going to be derived from the equilibrium of a simple element based on its stress state. And then the same in the y direction, this is equilibrium equation in the x direction, equilibrium equation in the y direction, we'll say partial nxy partial x plus partial nyy, partial ny of partial y must be equal to 0. Now we know that our nx, ny, and xy are actually related to midplane strains, epsilons, and epsilons are from linear elasticity, can be written in terms of the displacements. U, V, U displacement along x direction, V displacement along y direction, and then I can actually write these right there. Let's take a pen, make it blue. So epsilon x by linear elasticity is partial u partial x, okay, and then epsilon y partial v partial y, and gamma xy is partial u partial y plus partial v and partial x. Now if we put these into this equation and then take this equation and substitute in there, we get two partial differential equations for u and v, and we got rid of all the kappas, all the w's. There is no w displacement in these laminates. The two in-plane equations become these two. This is the x direction partial differential equation. This is the y direction equation. And it's somewhat lengthy, okay? But if you want to do the right analysis for your plate, you need to be able to solve these two equations, say for this case. And you need to also define your domain and boundary conditions and so on and so forth, so that you can solve out of these two equations u and v displacements of the midplane. There are no other displacement components. All the other displacement components are same as through the thickness, u naught and v naught for this case. So these are the unknowns, unknown displacements. Unknown displacements for the solution. Now, can you solve these for the uniform case? And the answer is yes. but we'll have to make some assumptions for boundary conditions. And the simplest assumptions are the variation. If nothing varies, then everything is trivial solution. But if there are some boundary conditions, let me, for example, suggest, actually this may be something that we may want to do just for the sake of argument. Yeah. Let me make a sample problem. Let's say I'm gonna keep these for the time being and make a sample problem here. Let me duplicate this slide. I think it's worthwhile to spend just a little bit more time on this. And make up a problem that that things are not going to be uniform any longer. And the simplest one that we can solve, let's get rid of the shear. I was thinking of something that will have at least one-dimensional variation. We'll have to make. Now, this is not going to be easy. You still have. Let me see. If I constrain those, but yeah, no, I'm not going to make this. I think we'll need to solve these equations at some point, but I'll make up an example that we can solve it more easily. But there is something that I want to point out right away before we get to those. And I'm going to duplicate this slide if I don't want to lose them. All right. This still looks cluttered by the fact that there's partial x in here. If the A matrix is constant, which is typically the case in almost all practical applications, that the in-plane stiffness matrix is constant, is not a function of x and y, unless you have a patch in the laminate. So if you have a patch somewhere, the thickness is changing, then the A11 is going to be varying. But in most uniform thickness laminates, the A matrix is constant, which means that all these partials can immediately be moved inside. That is, this, let me get a pen. This partial sign, I can take it, pass it beyond A11 here, and this will become A11 times partial square U partial x square, and this will come here, A12 times partial V, partial square V, partial X, partial Y, and then this term again will come here and here. If A16 is also constant, it will become partial square U, partial X, partial Y, and partial square V, partial X square. So it will be a simpler partial differential equation, and there will be the similar quantities coming from this side, okay? And that means this will move there, there, and here, and here. So these, you will do the summation of these terms, and then a much simpler equation in terms of partial U and partial V. And we should be able to solve those for simple boundary conditions. And this is what I think I will do as maybe next homework problem, because I think you can solve these partial differential equations very easily with Mathematica. And I'll show you how to do that with an example. And then later on, we'll do the same thing when there's more complex problems that has also the bending end, which is the simplest case, is the cylindrical bending, which is the pure bending of plates. So this is basically what the concept is behind stress-based design. Be able to get the displacements using finite elements that solve partial differential equations, which literally, that's what they do. Finite elements are, it's a numerical technique to solve partial differential equations. In real life, there doesn't exist little elements that make up your chunk of your material in your real structure. It's notional. The methodology is just to solve partial differential equations. But these days, most people teach finite elements as if they are real elements of the material. They're not. They're just solving an assumption that you made in the governing equations or built into the finite element code that you're using. That's a little bit of a sidetrack, but it is what it is. So, any questions about this? So let's talk about homework problem number 3. If you don't have any questions. That's homework 3. And surprisingly, this looks a bit like the homework problem that you just did or doing. I guess the deadline is tonight. We have a rectangular laminate with uniform properties. A matrix is constant everywhere. Under the action of a uniform biaxial stress resultants, and including the shear, Nx and y and Nxy, and Nx is given to be 100 kilonewtons per meter along this edge, and Ny and Nxy can be some fraction of Nx, where those fractions controlled by alpha for Nx and beta for Nxy, and alpha and beta can vary between 0 and 1. So the most, all the loads existing is 100 kilonewtons Nx, 100 kilonewtons Ny, and 100 kilonewtons Nxy. These are the stress resultants. We're going to perform this analysis, which is basically we're going to say Nx is equal to Nx bar. for two different laminates. The first one is what we call a quasi-isotropic laminate. It has equal amounts of zeros, 90s, and plus minus 45s, and represented as 45 / minus 45 / 90 / 0. Having said this, actually, most people do this analysis or build these laminates not like this. But I'm going to actually change the homework assignment a little bit, and I'll tell you the reason why. But I'll also explain the two extremes. This is for the A matrix. This will make no difference. The change that I'm going to be making will make no difference for the A matrix. But I'm going to put the 90 here and 45 afterwards, and then 0. And the reason for this is the angle variation from here to here, 45, here 45, and here 45. Whereas if I put plus minus 45, there's a 90-degree jump between the two layers. And then from minus 45 to 90 degree, there will be another 90-degree jump. The larger the jump between adjacent plies, the more problems you can encounter with respect to interlaminar shear stresses, which we are completely ignoring, incidentally. And for in-plane, the layup change that I just made makes no difference in terms of the in-plane stiffness matrix. Second laminate is not quasi-isotropic. This is 4 times repeating and symmetric with respect to midplane. So there's a total of 4 times 4, 16 times 2, 32 layers in the layup. This is also 32 layers in the layup, 2 symmetric, but it is plus minus 4, 5, 90, 30, 0, minus 30, 0, 90. And I'm also going to move 90-degree ply here and get rid of the 90-degree ply from here. So that now the jump is 45 degrees here, 45 degrees here. And then here it's between the, I could have done minus 30 or plus 30. I'll do plus 30, 0. It's 30-degree difference here and 30-degree difference here. And then another 30-degree difference here. And then a 90-degree. So there's a 9-degree jump between these layers. Do I want to also move that perhaps between these 2 layers? It's an option that should be considered, but that will change the bending matrix considerably. So moving the 9-degree from here to, let's say, here will make no difference in the A matrix. Okay? So for that reason, I'm going to move that here. Maybe later on when we do all right. So now there is no 9-degree jump inside here, but since this is the midplane, there are 2 layers of the same orientation, 0 degree at the midplane. So these 2 laminates that we're going to be analyzing, and we're going to be asked to determine the stresses in the principal and directions in each layer. For alpha and beta equals 0, so just nx. And then 2 other combinations of alpha and beta. You can take alpha equals 0.5, beta equals 0.5. Or that's one combination. You can take alpha equals, say, 25%, 0.25, and beta equals 0.5, or vice versa. Just 2 other combinations. Of course, if you want to use manipulate to put alpha and beta parametrically in there and be able to show the stress variations as a function of alpha and beta, that'd be also very good. But at least I want once for alpha equals 0, beta equals 0, and then two other combinations. Assume the material to be glass epoxy with the following properties. And layer thickness, I forgot to put. Layer thickness T to be equals to, let me make that italic. To be 0.00001 meters. So, yes, I think there's a question or a text. Is there a question? No. So this is meters, this is centimeters, millimeters. That's too small. Let's make it a little larger. 0.1 millimeters. Okay. And E1, E2, G1, 2 are gigapascals. Okay. This is the homework problem. Now you want to know how to solve the homework problem. Let's go and do it. What do you say? This will be the tutorial. Right, so I'm gonna save this homework assignment, and it's due a week from today. Again, midnight. And electronically submitted. So let's close this. All right. So I'm going to go to a tutorial for stresses. And this tutorial, folks, does not exist. And we're going to make it right here so that we will be able to say help. I'm getting the feedback that there are still people who are having a little difficulty with the Mathematica. There was a Bing. Is there a message in the Bing? I have a question. Concerned about homework 2 or really Mathematica in general. I am confused how to you're inputting the data from homework 2 or 3 and what our solutions should look like as an output from Mathematica. Yeah, I'm having the same problem figuring it out. Okay, so your homework problems could be like my notebooks. Now, I don't know if you download my notebook, if the formatting also comes with it, with all these cell colors and so on and so forth. So if it does, all you have to do is, okay, let's do that. You don't have to. I don't have to have this, but I know you'll need to activate and run your Mathematica. So you will do that. So you don't need to keep this cell. All right. And by the way, is this going to help? Is this helping you now? Or are you at a point that you cannot even download the tutorial that I have and start editing it? Is this going to help? Okay. So, all right. So you don't need this part of it. The only thing that you have to make sure when you delete this cell is to be able to check if the composites is going to be responding. For it to be responding, you'll have to have the program executed. So I'm going to open the programs. So this was the program file with the WL extension, and make sure that version 1, you have the version 1 downloaded. I've actually edited as late as, when was it? We had an office hour, and during the office hour I found a couple of typos that I corrected. So you have to run this code by clicking on it, and then you can forget about it. But once you do that, when you type composites, question mark, it comes back and says, okay, you can use these modules. Now, all of these modules now are available for you. Okay? So, we assign the material property to be glass epoxy, and the function that I need is apply properties. So what was apply properties? I needed the property of apply. So I can type apply, and by the way, as soon as I type apply, these functions that I already executed, they appear. I can choose one of them. Okay, so apply properties says no, this is the wrong one. Not apply, but apply properties. Apply materials, constituent materials. So this is basically a material and option. So this is, since we have a material property defined for your homework problem and for the homework problem that I just assigned. Okay, we're gonna put here my material equals, oh, this is a text cell. I shouldn't be doing a text cell, but I should be doing a executable cell. But I can, of course, write text in here. Yeah, actually, let me keep that. Okay, so I'm doing a homework problem. I'm writing things just like you should be doing, and I'm using my properties to store. but you can use any label that you want. And I expect you to personalize your own homework problem so that they will not look like each other. if you know what I mean. So I will say constituent properties. And I will say, I think less epoxy. And Kazakh says, no, you can't do that. You can only put S-class, for example. Then I will change it to S-class. By the way, this is completely up to you. You can choose a different material yourself if you like. Choose your own material out of this list. So it gives me E1, E2, G12, nu12. Okay? EG new. If it is return, it will give me. Oh, this is not the. This is still the apply property. Constituent materials, apply properties, apply materials. Let's see. What am I looking for? No. I want apply materials. Material and option. Yes. Apply materials. That was something else. This is constituents. I don't need the constituents for this. I need apply materials. And that's why this was less epoxy. All right. The only issue here is we have a metric problem, and default is conventional units. So option is metric units true. Was it the default? All right. So this is now metric units. So metric units, you can you say true or false. If you say false, it will give you in the conventional units. But for the homework, it is true. All right. Do I need this relationship in your homework assignment? I do. It's the Q-bar matrix, okay? Because stress state is given, we are going to be requiring or the orientation of a layer. So we have this sigma x, sigma y, tau x, y given. We're going to be computing these. So what else is given? Stress state at A. And for zero orientation. Okay? You can use your own label. And it will be best if you say, I will provide the specified stress state in the following. You put a statement as if you're writing by hand, typing a little text explaining what you're doing. So the homework problem, let's go to homework problem definition. Where is the homework? Homework is here. To second homework problem. And I'm going to make up a completely different one so that You don't have to. Okay. So for 0 degree orientation, well, let's make it the 30 degree. You can make your own labels for yourself, for the others. And of course, you don't have to use my labels here. This is just a label. I just came up with that. If you want something more descriptive, something that you find easier to do, for example, like escape sigma that's sigma. Okay? And if I want subscript, I have to do command underbar, no, control underbar, put the symbol X, come up. That's a new label. This is a different label. And it looks very complicated, but it's another label. Or this looks complicated. Depends on what is more, what's easier for you. Of course, you also need to specify which point that you're going to do. I can put a superscript in there and put a label A. So sigma X at superscript A. Or this is not such a good place for it. I can put superscript after X, control caret A. There it is. All right, what was this value? Sigma X at A, 150 gigapascals, right? Did we say giga or mega? Well, let's say megapascals. So sigma XA was megapascals. This was 100. All I did is assigned 100 to stress state A, and this tells me that I cannot actually make an assignment to this variable because it's protected. So there may be a reason for that. I don't know why they protect something like this, but let's get rid of that. Sigma X, 150 million. Okay. For some reason, they protected the superscript version. So, but I don't need both of them. I'll just use this 150 10 to the 6 stress state. This is sigma X. What I can do, I can put sigma X, sigma Y, and say tau XY 100 times 10 to the 6. I stored all of them into a list instead of assigning one by one X and putting another label X, Y, and tau XY. I said stress state at point A for 30-degree layup is this. That's an assumption that I made. So what do I need? I need from this the epsilons. So the relation between epsilons and this is Q bar matrix. So stresses and strains in an orient layer are related by this equation. But since we are given the stresses, we will need to invert this relationship to compute strains. So what is the Q-bar matrix? Q-bar matrix, you give the orientation angle and provide the invariant material properties, and you get the Q-bar matrix for that orientation angle. But I don't have the invariant properties yet. I have the properties, my properties. Okay? So what are invariant properties? Question mark. In U invariant. Invariant U or invariant? There's a lot of Mathematica building ones based on the invariance. So let me type in invariant U. Finally, it came out. It takes E1, E2, G2, provides the U1 through U5. So my U is equal to invariant U, and oops, my materials, what did I say? My properties, what did I assign my material properties to? My properties. Copy this, put it here. This is the U. So now I can call Q-bar matrix. I'm going to cut this off from here. Okay, that's my U. All right. My QB, affectionately called my QB, is equal to Q bar matrix. And this was 30 degrees. And this was my U. And this is the matrix, Q bar matrix for 30 degree ply. Okay? If you want to see this in matrix form, you can say matrix form and put my QB. This is the matrix form. So my strains is equal to, I need to invert the Q bar matrix. And take a dot product of it with the stress vector, which I called that. So where am I here? Let me make it a little bit more clear. At point A, 30 degrees, this is my strains. That's it. This is your homework problem. Now, of course, we showed that you can visualize these things. So this strain state, I can visualize it to see what visualization modules are there. I did not put them into this list. Do I have these plot laminate modules, plot laminate element, plot moduli. There should be layer element too, plot layer element, I think. So this was in the tutorial, one of the other tutorials. So let me see if I can actually find it. Plot layer element, yes, that is correct one. But just in case, question mark, plot, there it is, layer element. And it says, can be used to visualize. You can do only the undeformed element, or undeformed element with an orientation theta, or an element with strain state given, or strain state given, and also the angle to show. So I'm going to use this version. Okay. So if you made a Mathematica script similar to this, obviously with our numbers and labels, would the script file be all that we submit? Or would you prefer a document with the answers? As long as you say, this is my first answer, you point out that you just didn't do only, but you highlighted your result, you typed it with a text cell, just like doing paper and pen. You write something with pen, and then you make it a square on your answer. Now, if you don't know how to make a square on your answer in Mathematica, then boldface it or write it into a new text cell saying that. Let me show you. Let me copy a text cell. I'll copy this text cell here. Okay. And I will put that text cell here. Get rid of this figure from the text cell. Or answer for strains at point A. And you can copy this and paste it into a text cell. Put a little bit spacing so that we can actually see it. If you want to write in front of it epsilon x, epsilon y, gamma xy. I'm going to actually not make it anything fancy, but just put a list equals. There it is. If you want to color this or highlight this or make it boldface or whatever you want to do, it's all up to you. Make these fancy instead of x, putting a label like that. If you do escape, epsilon, escape, not on, but on. Come on, n. It puts an epsilon in there. If you do control underbar, puts a script. Put an x, control space, gets into the bar. Okay? These are all formatting things. If you go to palette, basic math assistant, classroom assistant, writing assistant, let's get the writing assistant. All right? And here comes a panel from that into other screen. This is the panel that comes up. Make it large. Here's your assistant for writing. Title cells, text cells. If you want a palette for basic math or yeah, let's put the basic math assistant. Where did the basic math assistant go? Here it is. I'll move it here. Make it 200. This is your basic math assistant. You can use every one of these in this in here. So, for example, there is epsilon y. I'm going to pick this one, and subscript already generated there, and I'm going to put y, and I'm going to highlight epsilon x, and come here and see if I can find say alphas and betas. So there should be some epsilon somewhere. There it is, epsilon. So epsilon y. And I'm going to make this gamma. Go to my assistant. Here's gamma. And I'm going to make this the subscript of gamma. So I'll go here, there, and type there x, y. All right, it's fancier. Depends on how fancy you want. So those are the palettes from the help. So plot, I was going to use this version of it. So I'm going to copy this from here to here, but it has those unwanted quotation thingies. Plot layer elements. Here I'm going to put what my strings A03 whatever. Most likely it will complain about the font, but we don't know. No. Okay, it didn't. So this is the undeformed shape. The black one, square. And this is the deformed shape after those strains. Now this also has an optional argument that says scaling factor. No, it's not scaling factors. Mohana, you might be able to remember this. I think you went through this. Do you remember scaling factors? Did I get it? Oh, okay. Default is, I think, 100 with 50. No. Let me do this again. Yes, plus layer element. I want to find out if this is because of formatting or. Yeah, so this is a scaling factor of 50, so the formatting here confused the statement. And if you want, you can make this 10, but as you make it smaller, so scale factor 1, you don't scale at all. You can hardly see the deformations. If you want to see something, you better use some scaling factor. Okay? It's already for 10. I think we are way beyond our class time. Do you have any questions? Let me see. So if he made answers. Yeah, I think that question was answered. Any other questions? All right, that was apparently helpful. I'm gonna still prepare another tutorial and post it for stresses, where I'm actually gonna show how to plot through the thickness stresses in one plot. You have everything to do homework problem number 3, but there is another plot functionality that I'm gonna mention. Can you please scroll up to 105? Yes. All right. Benjamin, what do you have in line 105? What do you want to ask? This is U, invariant material properties, U1, U2, U3, U4, and U5. That's what invariant U returns. Now your version, composite limits. I basically, first thing that I ran was this composite, and here there are some text that comes, apply materials. I think there's and it's confusing. These are the material modules. This computes invariant material properties. This computes mu2, from given E1 and E. I think these bring some confusion between constituent materials. These are the fiber and matrix materials that you can have. Ply properties is a module to give you property of a ply made of both resin and fiber. And then ply materials are the materials that you can use for a ply. But yeah, it's, you need to type question mark in front of each one of those and look at them one by one to see which one is doing what. All right. Any other questions or anything else? In which case, time to say adios and do свидания.